Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how to predict spontaneous redox reactions and to sketch electrochemical cells. So let's get into this. So we have a couple of examples I want to go over. So the first one is iron solid with magnesium 2 plus aqueous, uh, and that's producing iron 2 aqueous, uh, producing also magnesium solid. And then we have this reaction here with iron is with lead 2 ions and producing iron 2 ions and then producing lead solid. So the question is on the table. The question on the table is, will these be spontaneous if I put them together in a reaction, like in a chemical cell, right? So here's a picture of my chemical cell. Here I have an electrode. In here will be some whatever like ions involved, right? So the way to understand this is perhaps the solids are going to be my electrodes and the aqueous are going to be what's in the beakers. So if I have iron, let's say this is my iron electrode, then in my solution here I have magnesium ions. And then on this side I might have iron 2 ions plus a magnesium electrode. And if I have it set up that way, the question is if I close the circuit, if I push down the lever and connect these together, will electricity start to flow or not, right? Is it going to spontaneously go or not as it's set up according to the equation? Okay, so that's what we need to do. And so we need to remember that whatever is happening at the anode, remember the mnemonic device, a red cat and an ox, right? So this is going to be help us to remember that reduction occurs at the cathode and oxidation occurs at the anode. So red cat and an ox, right? So that's the other thing to remember. And I'll talk about this in a moment here, this neo-per. I'll talk about that in a little bit and how that mnemonic device works. So the first thing when you're trying to figure out whether or not this reaction is going to actually be spontaneous is you need to break it apart into its half reactions, its oxidation half reaction and reduction half reaction. So looking at the oxidation states, iron has a 0 oxidation state here, magnesium has a 2, iron has a 2, and then of course this has a 0. So iron here is going from 0 to +2, so it's losing electrons. Loss of electrons is oxidation. So remember, again, Leo-Ger or oil rig, to remember that. Okay, so here iron is being oxidized. It's losing electrons. So if we write that equation here, let's just write it over here in the space. So I have iron solid going to iron 2 plus. And if I balance that, it's losing 2 electrons, so I'll add the 2 negative electrons there. So that's one thing that's going on based on, I'm merely looking at the equation based on how it's written. We want it to go this way. And that the question is it going to spontaneously go this way? So in this case, magnesium 2 plus is becoming magnesium. So if we write that equation, so we have Mg 2 plus aqueous, and this is aqueous 2, right? And that's going to go to solid, right? So here, let me write this better. So this is going to be Fe2 plus aqueous plus 2 electrons. This is going to be Mg, and we're going to add 2 electrons here, and that's going to become Mg solid. So those are the 2 half reactions for this reaction here that we're trying to determine whether it is spontaneous or not. So now that we have our half reactions involved in this reaction here, now we can go to the cell potentials, the standard potentials in a table, right? So you would go to the reduction half reactions or the reduction electrode potentials that are usually in some table. And then what you want to do is compare the redox, or not the redox, the reduction standard potentials or electrode potentials for these two here, right? So we have iron and magnesium. So here is the table, and I just condensed it down to these 3, but you would find these on the table. And so you look for iron and magnesium. And so all of these are written as reductions. That's just the way the table is set up. So I'm going to look for magnesium and iron. So since it's written as reduction, I'm going to look for magnesium and iron 2 plus because that's what I have in my reaction. And what you want to see here is which one is higher on the table. And that's where this neo-per comes in. So neo-per stands for more negative is oxidation, more positive is reduction. So negative is oxidation, positive is reduction. So we're talking about more negative, more positive with respect to each other. They're relative to each other. It doesn't mean that they're positive or negative. They can both be negative. They can both be positive, but one might be more positive, one might be more negative. And so this is a mnemonic device to help us remember which one is going to be which one's going to be oxidation, which one's going to be reduction. So the idea here is that if you're higher on the table, you are going to be more reduction. Therefore, you're going to be more likely to undergo reduction than oxidation. So if I'm comparing iron and magnesium, here these two, you'll see that iron is higher on the table than magnesium. And also, you can see that magnesium is more negative compared to iron. So again, more negative is oxidation. So magnesium is lower on the table, right, than iron. So again, the way you want to think about this is the higher on the table you are, the more likely you are to undergo reduction. The lower you are on the table, the more likely you're going to undergo oxidation. More negative, so it goes from positive values to negative. So if you're more negative, you're more likely to undergo oxidation relative to anything that's above you. If you are more positive, then you're more likely to undergo reduction compared to things below you, right? So that's the thing you want to understand. So here you can see iron is higher on the table, therefore it's more likely to undergo reduction than this one. Another way you could think about it is think about electrons being negative, right? If electrons are negative, they don't want to go to the side that's more negative, right? So negatives, like charges repel, right? So if you've got negatives together, they're going to repel each other. So the side that has more negative is going to be the side that's going to more likely repel the electrons rather than attract them. So reduction is about attracting the electrons, right? And oxidation is about repelling or giving away the electrons. So we're trying to figure out which side is going to repel and give away. And so each side, each of these beakers here represent a half reaction. Which one of these half reactions is going to happen at the cathode? Which one at the anode, right? So, okay. So now that we got that kind of figured out, we look here. This is the way that it's written here. So we got these from this equation here. So we're trying to figure out, is this going to be spontaneous? Well, we already saw that since iron is higher on the table, that is the one that's most likely going to spontaneously undergo reduction. That means that magnesium is more likely to spontaneously undergo oxidation, right? So we would keep iron in this way, since iron is more likely to undergo reduction. It's more of a stronger reducing substance. It wants to, not reducing, but it most likely wants to undergo reduction. So this is what we want to keep in this way. So it's already written in the reduction form, we'll keep it that way. This one, if we're going to write the spontaneous reaction, we would have to flip this one, right? So, but look at what we have here. So in this case, the way it's written here, iron solid is going to iron 2 plus, it's losing its electrons. So this is being written as if it's undergoing oxidation, right? So in this way, it would undergo reduction. But that's not the way it's set up here. We would expect the iron to undergo reduction and the magnesium to undergo oxidation because it's lower. And so therefore, this is flipped in the other direction. So we would expect a spontaneous reaction of iron being reduced and magnesium being oxidized. So we would flip this. But in reality, what we're given is the opposite. So we would expect that this would not be spontaneous. So if we write our cell according to this equation here, so this is iron giving away the electrons, right? So this is undergoing oxidation. Oxidation happens at the anode. So oxidation, cathode, reduction. So iron here is going to give away its electrons. So what we would expect if we close this is that the iron would be, the Fe2 plus in solution would be reduced and form iron. And then the magnesium would actually be flipped. So the magnesium would give away electrons and be oxidized. So the way it would work, so the way this is written is not spontaneous. So if we were to make this the anode and cathode, the way it would really work is the iron here. So if the iron is being reduced, we would have, let's say this is our iron. So we're going to have iron over here. So we'll put Fe for iron. So we'd have our iron cathode, our electrode here for the cathode. The cathode would be made up of iron. And here we would have our Fe2 plus ions. And then for the anode, this would be our magnesium. And then in here we would have our magnesium 2 plus ions. This is the way we would set it up for it to be spontaneous. Or if we set this up, this is actually what's going to end up going to happen. So when we close this, since iron is less negative, it's more positive than the magnesium, it's going to attract the electrons, right? So the iron side is going to attract the electrons. So here's the iron side. So if we close this, the electrons are then going to spontaneously move in this direction here. So these are the electrons moving. And so the electrons are going to come from the magnesium. So the magnesium metal is going to give up the electrons. So the magnesium, so here's magnesium, it's going to give away its electrons and then form magnesium 2 plus. And then the electrons come here. The Fe2 minus in solution is going to pick up the electrons, right? So here it picks up the electrons, and then it's going to become more iron. And so that's what's going to happen when you shut the lever here and connect the circuit. So it's going to go in the opposite direction spontaneously compared to this one. It's not going to go in this direction. It's going to go in this direction spontaneously. So the way it was written is not going to be spontaneous. And so over time, this electrode is going to erode away because more and more magnesium is becoming Mg2 plus, and it's dissolving in the solution here. And then over time, this cathode is going to grow bigger and bigger because it's gaining more iron over time. So then also you can see that as time goes on, more and more positive ions are being produced. So this becomes more positive. And then this side becomes less positive because it's taking ions away from solution. And so over time, if you don't have a salt bridge here, then this battery is going to die. It's end up going to stop because this is going to become so positive that the electrons are not going to be attracted to here. It's going to be more attracted this way or less attracted this way. And so it's going to eventually stop. That's why you have a salt bridge here of something like with K plus and NO3 NO3 minus in here, so that as this becomes less and less positive, or more and more negative, right? So you're losing positive charge here. So then the positive ions will move this way to kind of replenish that positive charge. And as you gain more and more positive here, the negative ions will come over here to kind of cancel out that positive charge. So that'll keep the battery running a bit longer. All right, so that's it for A. What about B? Same thing for B. The first thing we want to do is write out the reduction and oxidation reactions as they're written. So here, iron is going to Fe2 plus. So again, that's the same thing here. So I'll write that here. And that's going to go to Fe2 plus aqueous plus 2 electrons again. And then for lead is going from lead 2 plus aqueous to lead solid. So we're going to have lead. So instead of magnesium now, we have lead 2 plus aqueous plus 2 electrons going to lead solid. So now we're going to compare these two in our table. So we got iron again, but now we're comparing that with lead. So again, we have both of these written as reduction reactions in our table. And so we're given the reduction electrode potentials here. And you'll see that lead is higher on the table than iron. This means that comparing these two relative to each other, the lead is going to be more likely to undergo reduction. It's higher on the table. It's less negative, so it's more likely to gain the electrons, right? So think of this as being more positive than this one. The electrons are negative. They are attracted to the more positive electrode, so they're going to go that way. So as it's written, we have this lead is going to undergo reduction, and if we see it here, it really is written here as reduction. So the way that we have it written here, it is going to be reduced according to the equation we're looking at, which is what we would expect. And then also iron, therefore, would be losing the electrons, undergoing oxidation. So since this is lower on the table than lead, we would flip this one to be oxidizing. So therefore, the way that this equation here is written for here, fits with what we would expect in a spontaneous reaction. So this actually would be spontaneous in this direction. So if we write our cell here, so then the lead is going to undergo reduction. So therefore, that's going to be the cathode. So in this case, instead of iron being the cathode, in this case, we would have lead. So we're going to have Pb and Pb. And so here we're not going to have iron 2 ions. We're going to have the lead 2 ions. And then in this electrode, this is going to be our anode. The anode is going to be iron. So here we have iron. And here we're not going to have magnesium. We're going to have the iron 2 ions. And so this is the way it would be for the spontaneous reaction for B. So this is spontaneous. So when we close the lever and have the reaction, the circuit complete, the lead will lose the electrons automatically, spontaneously sending electrons this way towards the cathode. And so the lead would pick it up and then form more lead. And the same thing here, the iron would be losing, the electrode would be losing iron atoms here to form the iron ions. And so this would be the spontaneous reaction. So for reaction B, it is written in the spontaneous way. We'd expect this to be spontaneous when we set it up this way. The anode and the cathode would be as it's set up. For A, it's not set up in this way, so this direction as it was would not be spontaneous. It would actually be spontaneous in the reverse direction. So I hope this was helpful. I know it was a little bit long-winded, but I hope the explanations made sense. If you like this video, if it was clear and very helpful or helpful in any way, please like the video, share it with your friends. Make sure you hit that like button. Also, subscribe to my channel, hit that notification bell, and when you do, click all so you can be notified by all the videos I put out. And finally, put a comment down below. Let me know what you think. If you've got questions, if you've got suggestions, let me know. I would love to hear from you. Thanks for joining me, and have a great day.